Hello guys, hello, good morning, a good, very good morning to all of you. कैसे हो आप? And how's everything is going? Good afternoon guys, a very good afternoon to all of you. This is our third session and second episode for the chemical reaction engineering in the series of interview preparation sessions. That that's what you can say simply SIPS 3, third SIP for us. This is something about me. On Unacademy, will discuss chemical engineering, thermodynamics, chemical reaction engineering, fluid mechanics, process calculation, and general aptitude with all of you. I'm teaching for the GATE chemical engineering exam, helping the students from 2013. I have studied my master's in IIT Delhi, and here some questions we have already done in our previous two sessions, like how does refrigeration slow down the spoilage of food, use of catalytic converters in cars, the design equation of CSTR, and how the back mixing affects the reactor performance. We also see the comparison of CSTR and plug flow reactor on the basis of back mixing. And we also talked about the advantages and disadvantages of each reactor type, especially batch reactors, CSTR and PFR. I give you some brief idea about this. The thermodynamic consideration, the reaction kinetics involved, the mass transfer limitations in the gas liquid reaction systems. So there you guys suggested me that we should have a proper session. So I will explain all of you these things. So we will have a session on this on Monday. Okay? Coming Monday, that is 27th May. That session will be on Unacademy platform. But still all of you will be able to watch it, since that is go I will make as a free session. We will talk about all these things in proper details. Okay, so stay connected on my Telegram group. You know the link. This is the link of my Telegram channel, and there you can find the information regarding this. Or you can join the discussion group of this channel, Gate PSU Insights. There also I will provide you the details, the link, and the timing of the session. So we will discuss all these things in proper details. By today evening, I will share the details with you on the group. Now, this was the question I did ask you to try by yourself how we apply the reaction kinetics and thermodynamics things, their concepts in the designing of nuclear reactors, and especially for the synthesis of nuclear fuels and reprocessing of spent fuel. And I did ask you to try this question as well, the exergy analysis for the chemical reactors and how the exergy loss can be minimized in the industrial reactors. And this was one question I did ask you to try by yourself, reaction engineering and thermodynamics concepts in the processes of cooking and baking, and the specific kinetic data, reaction data, if available with us for a given particular reaction, then how we can design a suitable reactor, how we will approach the problem, and what are the factors we will keep in our mind. I hope you have seen all these things. If you find any difficulty in any of these questions, tell me. I will explain here, or otherwise, we will move with the new set of questions today. Hello, hello, good afternoon, Abhishek, everyone. So, because I saw none of you mention anything in the comment section, I believe, I'm assuming you have seen all those things and you got the answer. Okay. Now, we will start our discussion today on these three questions. First, the temperature gradients in non-isothermal reactors, how they influence the reaction kinetics and reactor performance, and how we can control all these things. The next question for the day will be, what is Thiele modulus? How Thiele modulus signifies in the context of porous catalyst. And this is the third one. Sorry. Yeah, this was the first question of the day about the temperature gradients. And this is the third question for the day, about second question for the day about the Thiele modulus. How Thiele modulus signifies in the context of porous catalyst. And can you provide any example where optimizing the Thiele modulus leading us to improve the industrial process efficiencies? Okay. And this is the third question for the day will be, what are the key considerations we have to, what are the key points we have to think so that we can design a reactor for polymerization reactions. So we will start our discussion with this point about the temperature gradients and non-isothermal reactor stuff. So can any one of you tell me what is the meaning of non-isothermal reactors? First, and what is the meaning of temperature gradient? Question number six. Okay, so at the end of the session, we will also talk about the question number six. Here, what is the meaning of temperature gradient and how? What is non-isothermal reactors? Very well. So let's start our discussion. Non-isothermal reactors are those where along the length of the reactor, or you can then as along the space coordinates in the reactor, the temperature changes. Okay, or otherwise you can say non-isothermal reactors are those where the temperature changes during the process, during the reaction. While if I talk about the temperature gradient, so I hope all of you know that temperature gradient is a vector quantity. It helps us to figure out the variation in variation in temperature along a particular direction on a given location. मतलब रिएक्टर में किसी भी एक गिवन लोकेशन पे at any given location if you check you will get to know the direction of the temperature variation, like in which direction temperature is increasing or decreasing. So that's what we can understand with the help of temperature gradient. And if I ask you about the units, so you know that the units of temperature gradient in SI system, SI units will be Kelvin per meter. Okay, so this is something about the non-isothermal reactors and temperature gradient. I hope it is clear to all of you. Now, how the temperature gradient affects the reactor kinetics and reactor performance. Let's talk about that. So there are many ways. Effect of temperature gradient on reaction kinetics and reactor performance. So what are those effects? How we can study them? So first, about the reaction kinetics, if we say about the reaction rate. So all of us know that rate of reaction, that is R, we can write something like K product summation Ci power alpha I as per the Power's law. So you can see the rate of reaction is proportional to the rate constant K. And if you think about the Arrhenius equation, Arrhenius theory, so you know that rate constant K is the function of temperature. So during the reactor, even if you talk about, let's say, PFR, for example, if temperature changes are there, okay, so along with the temperature variations, along with the temperature variations, rate constant K, reaction rate constant K will vary, and that will affect the rate of reaction. How? Because it will make the rate of reaction uneven. You can say uneven rate of reaction will be there. This is first point regarding this. How the temperature gradient will affect the reaction rate. Are you able to understand this thing? Is it clear? Yes, guys, tell me, come on. Is it clear to all of you? How the temperature gradient will affect the rate of reaction, reaction rate constant, and everything? Yes, okay, wonderful. Now, second point is selectivity. This n- uneven temperature gradient, or you can say non uniform temperature gradient, can affect the role of selectivity in the formation of desired product. ठीक है? How you know that already? Suppose we have a parallel reaction A gives R, A gives S. Here the rate constant is K1, or forget about this. Suppose we have a reaction A plus B gives R having rate constant K1, and A plus B gives S having rate constant K2, where R is the desired product and S is the undesired product. So RR is equal to, suppose, K1 Ca power alpha 1, Cb power beta 1, and RS is equal to, suppose, K2 Ca power alpha 2 and Cb power beta 2. So you know that here, if you talk about the selectivity, so selectivity we can define in two ways. I hope you know that. One is overall selectivity, which is of no use in the optimization of reactions. And second is instantaneous selectivity. Overall selectivity used only in the material balance. ठीक है? Overall selectivity used only in the material balance. While if I talk about the instantaneous selectivity, it is used for the designing for the optimization of chemical reactions. For example, you can define it as rate of reaction for the desired product divided by rate of reaction for undesired product. So if you put these values, so you can see it will be something like K1 upon K2 power Ca, K1 upon K2 into Ca power alpha 1 minus alpha 2, and Cb power beta 1 minus beta 2. I hope you have seen this thing in the designing of multiple reaction system, designing of parallel reactions. So here if you guys see, like if I talk about, अब हम ये बात कर रहे हैं तो थोड़ा कंसंट्रेशन की बात कर लेते हैं, कोई इशू नहीं है, तो एक दो मिनट एक्स्ट्रा लग जाएंगे बस, बट आपका रिवीजन भी हो जाएगा. इफ अल्फा वन इज ग्रेटर देन अल्फा टू, सपोज, एंड बीटा वन इज लेस देन बीटा टू, suppose this is the case. So here you guys can see selectivity will be proportional to Ca power alpha 1 minus alpha 2 means positive, and Cb power beta 1 minus beta 2 will be negative for this case. So here you can understand, for high selectivity, for high selectivity, we have to keep high concentration of A, because if you increase Ca, selectivity will increase, and if you decrease Cb, selectivity will increase. So high Ca and low Cb we have to keep. Okay, so that's how you can understand the variation for concentrations, and how we can increase or decrease the concentration inside a reactor. You guys already know that. Okay, how to keep high concentration or low concentration. Think about this. Recall, if you want to keep high concentration, the first thing is, what is these concentrations? Where? At the inlet, outlet, or within the reactor? So I hope you understand all these things are based on rate of reaction. So these are the concentrations inside the reactor, within the reactor. So for high Ca, if you want to keep high Ca inside the reactor, we will prefer PFR, and for low Ca, we will use MFR. Why? Because you know that in case of MFR, concentration drop is very fast. So it is difficult to maintain high Ca inside the reactor. So that's why MFR will be used for low Ca, because of the fast concentration drop, and second, concentration within the MFR will be same as that of at outlet, that of at the exit. But if we talk about PFR, so you know concentration decreases gradually, so it is relatively easy to maintain high concentration inside the reactor. And if you want to keep high Ca inside the reactor, then you know that we have to maintain low conversion inside the reactor. And for low Ca, we have to maintain high conversion inside the reactor. You know that already. Low conversion and high conversion means basically the rate of reaction. If rate of reaction is high, conversion will be high, and if rate of reaction is low, conversion will be low. Third, if you want to keep high Ca inside the reactor, then you have to remove inerts from the feed. And for low Ca, you have to add inerts to the feed. Fourth is high Ca. If you have gaseous phase reaction, then you can keep high pressure inside the reactor. And for low Ca, you can keep low pressure inside the reactor. तो आई होप यू नो ऑल दीज थिंग्स, है ना? और कैसे करते हैं वो आप सबको पता ही है, हम ये बात कर चुके हैं. दिस इज द वेरिएशन, दिस इज हाउ वी कैन ऑप्टिमाइज द सेलेक्टिविटी विद द हेल्प ऑफ कंसंट्रेशन. नाउ इफ आई टॉक अबाउट द टेम्परेचर विच वाज द मेन पॉइंट ऑफ आवर क्वेश्चन, ठीक है? तो यू नो दैट फॉर टेम्परेचर selectivity is proportional to K1 by K2, and the reaction was something like this. So here you know that for first step activation energy will be E1, and for second step let's say E2. Because it is obvious K1 and K2 they are different, but the temperature has to be same. So obviously rate constant K apart from temperature depends on the value of activation energy. So for two different reactions activation energies are different. That's why the rate constant K will be different even for the same temperature. And if those two chemical reactions have same activation energy, same temperature, then rate constant K will be same, most probably. Otherwise, it is not necessary. क्योंकि एक्टिवेशन एनर्जी एंड टेम्परेचर सेम है तब भी रेट कांस्टेंट के डिफरेंट हो सकता है डिपेंडिंग ऑन द वैल्यू ऑफ प्री एक्सपोनेंशियल फैक्टर और यू कैन से आरएनएस कांस्टेंट. यू नो दैट ऑलरेडी, है ना? आरएनएस इक्वेशन क्या था? के इज इक्वल टू के नॉट इंटू ई टू द पावर माइनस ई बाय आर टी. So for two reactions, if activation energy and temperature are same, but this is different, still K value will be different. But in those two reactions, percentage change in K will be same. Percentage change in K will be same. So here, if you want to study the effect of temperature, so you can understand this entire reaction will takes place in one reactor. So if I increase the temperature, if I decrease the temperature, the variation of this temperature will be same in on both the steps. Okay. So how we will see how that temperature variation affects the selectivity. You know that we have to keep high selectivity, means we have to keep this ratio K1 by K2 high. So here to understand this, draw a curve between ln K versus 1 by T. If you remember from Arrhenius equation, this curve between ln K versus 1 by T was a straight line having slope minus E by R. है ना? I hope you remember this. The first case, let's say if E1 is greater than E2. So here you guys can understand if E1 is greater than E2, then the slope for K1 curve will be high as compared to that of for K2 curve. So here you guys can see if I increase the temperature, if I increase the temperature, then it is obvious that K1 and K2 both will increase. Okay, but you can see for this temperature rise, this temperature change, the percentage rise in K2 will be this much. While for the same temperature change, percentage rise in the value of K1 will be more, as you can see from the slope, since E1 is greater than E2. Okay, so that is the meaning. Means you can think like this. Suppose K1 and K2, their value is K1 is 5, K2 is 2. Suppose at some temperature T1. Now I have increased the temperature from T1 to T2. So K1 will and K2 both will increase. So K2 will rise and K2 value will be smaller. Let's say, see, rise in K2 value will be smaller. So let's say that is increasing only 1.5 times and increase from 2 to 3. But K1 has become double, suppose. So you can see the ratio. Initially, the ratio was 5 by 2, that is 2.5. Now the ratio has become 10 by 3, that is 3.3. So ratio has increased. So that's why if E1 is greater than E2, for high selectivity, we will keep high temperature so that the formation of desired product can be more as compared to undesired one. While if I talk about the second case, like if E1 is less than E2, okay, so you can also think about that in the same way. So here ln k versus 1 by t graph, if you look, E1 is smaller, E2 is higher, so obviously the slope of the K2 curve will be more as compared to that of for K1 curve. And now here you guys can see if I change the temperature, percentage change in K2 will be more as compared to K1. That means here if I increase temperature, then K2 will increase more as compared to K1. Both will increase, but K2 will increase more. So ultimately, because of this, you can understand the value of this ratio will decrease, which is not good for us because denominator is increasing more. Percentage change in denominators is high as compared to percentage change in K1. So that's why in this type of scenario, we will keep low temperatures. Because if temperature is low, then you guys can understand the percentage change in K2 value will be more as compared to percentage change in K1 value. मतलब क्या है आप इसे ऐसे समझ सकते हो K1 एंड K2 सपोज उनका वैल्यू K1 का 5 था K2 का 2 था at temperature T1. Now if I have decreased temperature, K2 will decrease more. Suppose K2 has become half, मतलब 2 से 1 हो गया. But K1 has also decreased, but उसमें जो decrease आया वो कम आया, let's say 4. It has become from 5 to 4. So you can see the ratio. Initially it was 5 by 2, means 2.5, but now it is 4 by 1. So ratio has increased ultimately. So here we will keep low temperature. So that was the point when we were talking about the variation in temperature gradients. So if temperature gradient is there, if we have uneven temperature gradient, so you can understand the values, the changes in K1 and K2 values will be uneven as well. And it is also possible that the selectivity may increase or decrease unevenly during the process. So obviously that will affect the performance, the formation of desired product. Because here you guys can understand K1 represents what? If I talk about K1 and K2, what is their physical significance in this scenario? So you can understand K1 is the rate constant for first step, reaction rate constant for first step, or you can say desired reaction or desired step, while K2 is the reaction rate constant for undesired reaction, or you can say undesired step. So that means if K1 increases or K1 is more very very larger than K2, so what is the meaning? That means that means the rate of formation of desired product, rate of formation of desired product will be very very larger than that of for undesired product. I hope this part is clear now, guys. how the selectivity will affect the reaction. How मैंने आपको ये भी बता दिया यहाँ पे extra how we can optimize the parallel reactions with the help of selectivity. And here I have also told you that how the temperature gradient affects the selectivity. है ना? So is it clear to all of you? Are you able to understand, guys? Hello? Hello, guys. I'm talking to you. Are you sleeping? Good morning. वैसे इतनी समर में मुझे नहीं लगता आप लोग सो सकते हो. क्लियर है? तो अगर ये आप सबको क्लियर है तो मेरा इसी में एक क्वेश्चन है सेलेक्टिविटी के ऊपर ही. हम टेम्परेचर की बात भी करेंगे. Suppose we have a reaction like A gives R gives S. Here rate constant is K1, here it is K2, and suppose R is my desired product. है ना? Here the order of reaction for first step is 2 and for second step it is 1. Activation energy in first step is let's say 90 and in second step let's say it is 120. So tell me now to maximize the yield of B, to maximize the formation of B, what shall be the initial concentration, high or low? Second, the reactor type, which reactor you will prefer? You have only two choices, CSTR and MFR. Okay. And third, the temperature. What we have to keep? Concentration CA naught shall be high or low. Reactor type CSTR or PFR, or otherwise the temperature high or low. What we have to keep? Answer. Think. Take couple of minutes. You can write your answer as like high CA, high concentration PFR, low temperature, or low concentration PFR, or low temperature, something like this. Think about this. Take 1 or 2 minutes. Okay, matrix, Tanmay, we will see. Yes, Sane Shekha. Come on, guys. Tell me. You said it is clear and you know that already. So now what shall be the answer? And if you guys are going to see in recording, so you can pause and think about this. Let me give you the answer. Here, what shall be the value of CA naught? It is obvious R is the desired product. R is the desired product and it is coming, producing from A. So it is obvious that CA naught shall be high because if CA naught is high, then obviously the desired formation of desired product will be high. अगर आप ज़्यादा A भेजोगे तो ज़्यादा R बनेगा, कम A भेजोगे कम R बनेगा, सिंपल. Simple. I hope it is clear now. You know. Now, if I talk about the reactor, so you can see A gives R follows second order kinetics. So you know that for chemical reactions having order of reaction greater than 0, we prefer PFR of same volume as MFR gives more conversion. Yesterday we discussed the reason of this with the help of back mixing concept. So obviously we will prefer PFR. That is my second point. And about the temperature, if you have to see, so see for the first step K1 activation energy is 90. For the second step K2 activation energy is 120. So obviously we have to keep low temperature. This is your third point. So high concentration CA0, PFR and low temperature. Why? Because if you increase the temperature, if you keep high temperature, then you can understand K1 and K2 if you draw that curve. Percentage rise in K2 will be more as compared to K1. That means disappearance of R. K2 is representing what? K2 is representing disappearance of R. The disappearance of R will increase. So we will not be able to maintain the correct amount, the high amount of desired product. That's why we have to keep low temperature. So when we will keep low temperature, then the percentage fall in K2 will be more as compared to K1. The rate of disappearance of R will decrease more as compared to rate of formation. So R we can sustain for a longer duration. We can maintain in high amount for a longer duration. So that is the point. That's how you can answer such type of questions. Okay. So is it clear now? I hope now it is clear. At high temperature, K2 is greater than K1. Okay, wonderful. Now let's get back to the our question. हमारा क्वेश्चन क्या था गाइस? हमने कहाँ से स्टार्ट किया था, कहाँ पहुंच गए? This was our question. How temperature gradients in a non-isothermal reactor influence the reaction kinetics and reactor performance, and what strategies we can employ means the preventive measures we can have if things goes out of control. So first was reaction rate, reaction kinetics. I told you how weak temperature gradients affect that. Second thing about the selectivity. I have told you, and I have also explained all these things regarding the selectivity and some common topic. Okay. Now, the third point about is third factor is conversion, or you can say rate of conversion. Okay. Like how the temperature gradients will affect the conversion rates, rate of conversion. Okay. So suppose we have a PFR. Let's say, think like this. Suppose it is one adiabatic operation. I am sending some feed, let's say A, and here we are supposed to get a product. Suppose the reaction is exothermic. So you know that exothermic reactions are those where the heat released during the reaction. But since it is adiabatic reactor, so you know that adiabatic condition means no heat exchange between system and surrounding. So here, whatever heat is getting generated inside the reactor, suppose feed was entering at temperature T1, and now whatever heat is getting generated inside the reactor, it has no place to go anywhere. So what will happen? Automatically, this heat will be absorbed by the reaction mixture itself. Heat will be absorbed by reaction mixture itself. That will cause the rise in internal energy of the reaction mixture, and that will lead us to rise in the temperature. So ultimately, the final temperature in the outlet in the product is, let's say, T2, which will be greater than T1. This is any reactor. It could be PFR as well as MFR. Doesn't matter. Okay. So suppose if this is a PFR, and if I look at the temperature variation in PFR, so here you know temperature is T1 initially at length equal to 0. Now, as the reaction is taking place, temperature of the reaction mixture is increasing. And generally, this variation occurs exponentially. I hope you know that. You have studied the Van Hoff equation, so you know that thing. Okay, if you guys know about the Van Hoff equation. Okay, so what will happen? Now understand. If I talk about the graph between equilibrium conversion versus temperature, so I hope you guys know that for endothermic reaction, the variation will be something like this between equilibrium conversion and temperature. And for exothermic reactions, variations will be something like this. So here you guys can understand for for exothermic reactions, we try to keep the reactions at low temperatures. So you can see, if you see the graph of equilibrium conversion versus temperature, like here, we have high equilibrium conversion when the temperature is low. So you can understand this. But here in this PFR, what is happening along the length temperature is increasing. Okay, so it is obvious along the length, if you look, the equilibrium conversion that will decrease. So if equilibrium conversion is decreasing, while you know that equilibrium conversion is nothing but the point value, the point conversion. So since equilibrium conversion is decreasing, so it is obvious the overall conversion will decrease, will be a smaller value. The actual conversion you can say, overall conversion you can say. And I hope you know that this overall conversion is nothing but a cumulative value. So you can understand like this. Inside the reactor, you can see here at inlet temperature is lowest in this arrangement. So as per the graph, you can understand for exothermic reaction at lower temperature conversion will be maximum. At, at this point, temperature increase, so equilibrium conversion will be less. Equilibrium conversion means the number of moles participating in the reaction. Here will be more, less, more, less, more, less, more, less, like this. So they are decreasing basically. Number of molecules participating in the reaction are decreasing along the length. That's why the equilibrium conversion is decreasing. That's why the overall conversion will decrease. So that's how you can understand about this. How the temperature will affect the things, will affect the overall conversion, basically the reactor performance. So I hope guys all these things are clear. So that's how you guys can understand this. Okay, so these are some three main points which you can use to explain the effect of temperature gradient on reactor performance. Okay, now if we talk about the strategies, how we can manage the temperature gradient and all in our benefit and all that stuff. So you know that here one more point if you wish you can add about the catalyst. Okay, due to the temperature gradients, catalysts can also get affected. Okay, the reactions may occur, unwanted reactions may start, और the catalyst may get degrade. ठीक है, या फिर हो सकता है catalyst पे fouling start हो जाए, basically catalyst deactivation. तो so many things are there. Okay, तो जब हम strategies की बात करते हैं अब to maintain the temperature gradients or to manage the temperature gradient you can say. So here we have many points which you can add. Okay, like you can talk about the uh, reactor design, you can talk about the configuration, you can talk about the catalyst management, you can talk about the reactor design or configuration. ठीक है, अब यहाँ पे हम बात करें पहले कैटलिस्ट मैनेजमेंट की. तो हाउ वी कैन मैनेज द कैटलिस्ट, दैट इज द क्वेश्चन. ठीक है, तो हम ऐसे कैटलिस्ट यूज कर सकते हैं विच आर थर्मली insulated, means thermally resistant, which does not have any effect of temperature variation on them. ठीक है, मतलब क्या है, अगर सपोज हाई टेम्परेचर है तो वो विद स्टैंड कर लें, लो टेम्परेचर है तो उस पर कोई इफेक्ट ना हो। हम कैटेलिस्ट का डिस्ट्रीब्यूशन मैनेज कर सकते हैं कि लाइक रिएक्टर के एंट्रेंस पर हम ज़्यादा कैटेलिस्ट रखें और एग्जिट तर आते आते कम कैटेलिस्ट रखें, लाइक दिस अलोंग द लेंथ। कैटेलिस्ट लोडिंग जो है, इसे हम कैटेलिस्ट लोडिंग बोलते हैं। ठीक है, तो वो आप समझ सकते हो। वी कैन मैनेज द कैटेलिस्ट लोडिंग, वी कैन मैनेज द कैटेलिस्ट, वी कैन चूज सुटेबल कैटेलिस्ट। ठीक है, suitable catalyst like suppose if we have exothermic reaction, so you know that exothermic reactions means temperature rise has to be there due to the heat release, and if temperature is increasing, so it is possible that we might that rise in temperature may create some hot spots on the catalyst surface. ठीक है, which can lead to the catalyst deactivation or otherwise in the fouling or the catalyst degradation. ठीक है, similarly if we are having endothermic reaction, so it is possible that on the catalyst surface we might have some cold spots, and cold spots can cause the reduction in rate of reaction. So many things are there, guys. That's how we can manage the catalyst, है ना? And similarly if we talk about the reactor designing, so reactor designing is all about basically the heat exchange. You know that when we talk about the isothermal reactors means how we will operate a reaction in isothermal mode, how we can maintain the isothermal conditions. So you know that suppose we have a reactor, temperature is 30. If exothermic reaction is there, heat will rise, which will absorb by the reaction mixture itself and increase the temperature. Even if the reactor is non-adiabatic, so it is not guaranteed that whatever heat is getting released, all of that heat will be released in the atmosphere into the surroundings. Some part of that heat might also may also can be absorbed by the reaction mixture itself. The ideal scenario will be whatever amount of heat is getting generated, if we are able to remove all that heat. If we can remove all that heat, then obviously the reaction mixture will remain at the same temperature. ठीक है, तो अब वो हीट हमें रिमूव कैसे करना है? Similarly if it is endothermic reaction, so whatever amount of heat is required during the reaction, same we have to provide. So when you will provide the same amount of heat, ultimately the temperature fall will not be there. Why temperature falls during endothermic reaction? You know that if it is adiabatic reactor, endothermic reaction, you are sending temperature at inlet is T1. So you know endothermic reactions means reaction will require some heat during the reaction, but we are not supplying any heat due to adiabatic condition. So what will happen? Reaction mixture will start to consume its own internal energy, because of which the temperature will fall. जैसे आप ऐसे समझ सकते हो कि अगर आप लोग हंगर स्ट्राइक पे चले जाओ, still you will not die for some days. Why? Because the energy needed to sustain your body or all the stuff needed, the daily routine of your body will be consumed. Body will consume from the energy stored in your cells. After some time, there will be a problem, but initially there will not be. Similarly, in endothermic reaction, mixture will start to consume its own internal energy, the stored energy in that will cause the temperature fall. तो अब क्वेश्चन आता है हम कैसे टेम्परेचर को हाई या लो रख सकते हैं? हम कैसे हीट को सप्लाई या रिमूव कर सकते हैं? तो बहुत ही सिंपल है। रिएक्टर का डिजाइन हम इस तरह से कर सकते हैं, लाइक इफ यू नो द कॉन्सेप्ट ऑफ गीजर, थर्मल गीजर्स, हाउ दे वर्क, ओके, और अदरवाइज The induction rod we use in winter days to heat up the water. Sorry. So that type of things you can use. Okay. तो हम रिएक्टर में coil भेज सकते हैं to generate the electricity, to generate the heat with the help of electricity. Otherwise we can design a reactor in such a way कि reactor के surroundings में हम jackets create कर सकते हैं, and we can supply cooling water or steam or hot fluid whatever is needed as per the requirement. ठीक है, ये हमारे दो पॉइंट हो गए. नाउ फर्दर आपका थर्ड पॉइंट आ जाएगा हीट एक्सचेंज. अब वो आपने हीट ट्रांसफर में पढ़ा होगा. हाउ कैन यू ऑप्टिमाइज द परफॉर्मेंस ऑफ हीट एक्सचेंजर्स. So here you can optimize the heat exchange thing when the heat is being exchanged between the reaction mixture and the process utilities. ठीक है. Or otherwise you can talk about the controllers, the process controllers you can use, the suitable process controllers. ठीक है. How process controllers will affect the things, you know that. अगर हम feed forward या feed backward controllers use करते हैं, you know how they affect the things. Set points, disturbance, advanced control strategies you can use to monitor the variations and control them, or to maintain the optimal temperature throughout the reactor. There are so many things we can do. Okay, so that's how we can manage the temperature gradients inside the reactors. Okay, so I hope it is clear now, guys. So this is something about the answer of this question which I just told you, which I just explained in a detailed manner. इन फ्रॉम द पॉइंट ऑफ व्यू कि आपका मल्टीपल रिएक्शन सिस्टम का कॉन्सेप्ट, सेलेक्टिविटी का कॉन्सेप्ट भी रिवाइज हो जाए, एंड नॉन आइसोथर्मल रिएक्टर का जो बेसिक थ्योरिटिकल पार्ट है वो भी रिवाइज हो जाए. ठीक है, तो आई होप ऑल दीज थिंग्स आर क्लियर नाउ. Okay, now the next question here is about the Thiele modulus. So we will talk about that. So all this is clear to all of you. Someone of you was saying yesterday, okay, if we talk about non-isothermal reactor, that would be better. So any one of you have any other preferred topic from CRE? Because tomorrow we will have the last session of CRE in this series. And from next week, if it will be allowed, if it will be possible, then we will start our discussion on some other topic, other subject. Okay. तो सीआरई में अगर आपका कोई और प्रेफर्ड टॉपिक है तो आप यहाँ पे मेंशन कर दो लाइव चैट में. आई विल ट्राई टू कम विथ सम गुड क्वेश्चंस related to that topic. Hello guys, do you have anything to discuss? In case if you find any, you can mention. So now let's start our discussion on this question. What is Thiele modulus? So you know that Thiele modulus is a dimensionless parameter used to relate the pore surface reaction and pore diffusion rate. Surface reaction rate and pore diffusion rate and can be denoted by phi or mt, which can be defined as K over D, or you can write DAB multiply by L. Or you can also define like surface reaction, square root of surface reaction rate divided by pore diffusion rate multiply by characteristic length. And generally, you know that this characteristic length will depend on the size of particle, size of the pore. Okay. Like for cylindrical particle, it is R by 2. For spherical particle, it is R by 3. Like this. You know that. Okay. Now, the second point is how does Thiele modulus, what is the significance of Thiele modulus? Or you can say in the context of porous catalyst, how it will signify the things. So in porous catalysis, you know that Thiele modulus, when we talk about the Thiele modulus, it has, we can define like high Thiele modulus, low Thiele modulus, something like this. Okay. Basically, Thiele modulus signifies the rates, the related relation, or you can say the dominance of the pore diffusion rate or surface reaction. Which thing is controlling the process? Which thing is dominating the process? We can get to know with the help of Thiele modulus. ठीक है, ये हमें बताता है कि आपका जो लिमिट कंट्रोलिंग स्टेप है, रेट कंट्रोलिंग स्टेप, और यू कैन से द रेट लिमिटिंग स्टेप कौन सा है, पोर डिफ्यूजन रिएक्ट रेट है या फिर सरफेस रिएक्शंस है. ठीक है, तो वो आपको पता ही होगा. ठीक है, वो हम यहाँ पे देख भी सकते हैं, ये आपने किया भी होगा. लाइक थिले मॉडुलस इज समथिंग लाइक दिस, you can see. So if Thiele modulus is high, if we have high Thiele modulus, so you guys can see here, it will be possible only when K is high, means surface reaction is high, or you can say fast reaction, fast surface reaction. Second is it will be high when D is small, means pore diffusion rate will be low. Or you can say slow diffusion. And third, large pore size. On the other hand, if I talk about the low Thiele modulus, so here you guys can understand K will be small, means you can say slow reaction, fast diffusion, and small pore size, or you can say short pore size. Okay, so here you guys can see surface reaction rate in this case. Now, remember one thing, guys. This is one note, which one important point all of you should know. Okay, if you have to use the Thiele modulus to figure out the rate controlling step, the rate limiting step, so always think or visualize with the help of pore diffusion resistance. ठीक है, पोर डिफ्यूजन रेजिस्टेंस की बात हो रही है. पोर डिफ्यूजन रेजिस्टेंस के रेस्पेक्ट में ही विजुलाइज करना है, वो आपके लिए हमेशा यूजफुल होगा. ठीक है, कैसे, तो उसकी बात करते हैं. So here you guys can see if Thiele modulus is high, the pore diffusion rate is small. And you know that generally we can define flux as the ratio of driving force over resistance. And what is flux? You know that we can generally define flux as rate per unit area. है ना? So ultimately you can see rate is inversely proportional to resistance. Sorry. So small pore diffusion rate, slow pore diffusion means high pore diffusion resistance. So this will be termed as the step of SPDR. Maybe you know, strong pore diffusion resistance regime. ठीक है? And here the rate controlling step will be pore diffusion, because you have to understand the step with highest resistance will be the pore diffusion rate controlling step always. Here you can understand fast diffusion, so slow reaction, so resistance due to reaction will be high. Obviously the rate controlling step will be surface reaction. And here if you look, pore diffusion rate is high. That means the pore diffusion resistance is low. So this is generally termed as diffusion free regime. Diffusion free regime. डिफ्यूजन फ्री से हमारा मतलब यहाँ पे ये नहीं है कि डिफ्यूजन नहीं हो रहा है. डिफ्यूजन फ्री मीन्स द इफेक्ट ऑफ डिफ्यूजन इज ऑलमोस्ट नेग्लिजिबल. डिफ्यूजन इज नॉट कंट्रोलिंग एनीथिंग. ठीक है. इट इज सम जस्ट सिंपल लाइक व्हेन वी सेड इंडिया हैज बिकम इंडिपेंडेंट इन ऑन 15th अगस्त 1947. हमने क्यों बोला कि इंडिया हैज बिकम इंडिपेंडेंट? बिकॉज नाउ ब्रिटिशर्स हैज नो कंट्रोल ओवर इंडिया. ठीक है. तो सिमिलरली हियर डिफ्यूजन हैज नो कंट्रोल ओवर प्रोसेस, मींस diffusion resistance is weak, so it has no control. So diffusion free design. That's how you can understand this. I hope it is clear to all of you now. है ना? तो ये थोड़ा हमारा सिग्निफिकेंस के बारे में था कि how we can talk about the Thiele modulus, how we can signify the give the significance of Thiele modulus and all these things. तो एक बार आप देख लो, चेक कर लो, सोच लो माइंड में हुआ क्या. और अगर आपको कोई डाउट हो तो आप लोग पूछ सकते हो. अदरवाइज वी विल टॉक अबाउट द थर्ड पार्ट ऑफ दिस क्वेश्चन. This was the question, if you remember. How we can optimize the Thiele modulus to increase the efficiency of industrial reactors, industrial processes. ठीक है. तो अब इसके ऑप्टिमाइजेशन की बात करते हैं. तो एक एग्जाम्पल से समझते हैं. All of you already know this. Suppose if I talk about the Haber process. This is one very basic example. Everyone know about this. Where nitrogen reacts with hydrogen to give ammonia, and the catalyst particles are used generally iron. ठीक है. To think, suppose if we have large size catalyst particles, large size catalyst particles, then what will happen? So here you guys know how catalytic reaction occurs. Those 7 steps, I hope you know that. First, the molecules will move from gas phase to external surface of catalyst. Then from external surface of catalyst, they will diffuse inside the pores of the catalyst. Then the adsorption, surface reaction, desorption, then diffusion from inside the pore to external surface, and then from external surface to gas bulk again. ठीक है, तो सपोज अगर हमारे कैटलिस्ट पार्टिकल्स लार्ज हैं, ठीक है, वी हैव लार्ज कैटलिस्ट पार्टिकल्स, सो व्हाट विल हैपन टू द डिफ्यूजिविटी? कैन यू थिंक अबाउट दैट? Okay, never mind. So think like this. Suppose we have a scenario. Suppose we have a case where we have large size particles and one is the case where we have small size particles. So suppose if we have large size particles and one is the case where we have small size particles. So now just understand this with one simple example. Think like this. I hope now it is clear. Suppose here molecules are moving from this side. So, and here also. So now you see this. The first step was molecules will move from gas phase to external surface of catalyst and then from external surface of catalyst to pores. So here, this is the external surface of catalyst. Molecules has reached here. Now the second step. See, in this case, I hope you know what are the pores. Pores means what? The empty space between the molecules, the voids between the molecules of solids. These are the pores. है ना? I hope you know that. So here, when we have large size particles, to see, molecules has to travel a large distance. You can see, molecule has to travel a large distance to enter inside the pores. But if we have a small size particle, you can see molecules will enter in the pores directly. The distance traveled by the molecule for second step will be small. Okay. So I hope you can understand this. In large size particles, molecules has to travel longer distances. Travel longer distance to enter the pores. And you guys know that if the travel path is long, then the resistance will be high. That means the diffusion resistance will be high. And if diffusion resistance high, then you can understand the Thiele modulus will also be a high value. ठीक है. और अगर डिफ्यूजन रेजिस्टेंस हमारा हाई है, थिले मॉडुलस हमारा हाई है, तो इस केस में क्या होगा, जो हमारी रिएक्शन है वो डिफिकल्ट हो जाएगी. क्योंकि रिएक्शन कह रहा हूँ, सॉरी, एफिशिएंसी जो है प्रोसेस की वो डिक्रीज हो जाएगी. प्रोसेस एफिशिएंसी, और यू कैन से द कैटलिस्ट एफिशिएंसी विल decrease. Why? Because you can understand very less number of molecules. High Thiele modulus means diffusion resistance is high. That means very less number of molecules are able to enter inside the pores. ठीक है, मतलब मेरे पास ये कैटलिस्ट है, तो यहाँ से मॉलिक्यूल्स आए बट बहुत ही कम मॉलिक्यूल अंदर जा रहे हैं. मोस्ट ऑफ द मॉलिक्यूल्स विल स्टे एट द एक्सटर्नल सरफेस. Very less number of molecules will be able to enter inside the pores. So it means the utilization of catalyst surface, the surface area of the catalyst will be very less. So ultimately the rate of reaction will be, overall rate of reaction will be less. Means process efficiency will be less. So I hope you have understood this. So this is the first thing we have to keep in our mind, that the catalyst particles we are using shall be small size. That's why we preferred small size catalyst particles. ये क्वेश्चन भी आपसे पूछा जा सकता है. Why we prefer small size catalyst particles, not the large size? So one answer is this, and you can explain with the help of Thiele modulus, और अदरवाइज वही आपका मैकेनिकल ऑपरेशन वाला आंसर जो सभी लोग बोलते हैं कि स्मॉल पार्टिकल्स, स्मॉल पाउडर, लार्ज स्पेसिफिक एरिया. अरे तो लार्ज स्पेसिफिक एरिया है, ठीक है, बट अगर आप इस तरह से आंसर दोगे टेक्निकल वे में, दैट विल शो यू, दैट विल रिप्रेजेंट, दैट विल इंडिकेट दैट यस यू हैव अ गुड नॉलेज. ठीक है, तो आई होप इट इज क्लियर नाउ हाउ थिले मॉडुलस you can use the concept to explain the size requirement of catalyst. Okay, नाउ नेक्स्ट आगे बढ़ते हैं. जब हमारा और इसमें और भी चीजें हैं आपको अगर ऐड करनी है, तो अगर लार्ज साइज कैटलिस्ट पार्टिकल्स हैं तो यू नो पोरोसिटी विल बी स्मॉल, टॉर्चोसिटी वुड बी देयर, नॉन यूनिफॉर्मिटी ज्यादा होगी ना. छोटे छोटे पार्टिकल्स हैं तो वहाँ यूनिफॉर्मिटी फिर भी हम एक्सपेक्ट कर सकते हैं, बट लार्ज पार्टिकल्स में नॉन यूनिफॉर्मिटी ज्यादा होती है, तो टॉर्चोसिटी विल इंक्रीज, है ना. तो इफेक्टिव डिफ्यूजिविटी क्या होगी, वो हमारी कम हो जाएगी. क्योंकि आपको पता है इफेक्टिव डिफ्यूजिविटी इज इनवर्सली प्रोपोर्शनल टू टॉर्चोसिटी एंड डायरेक्टली प्रोपोर्शनल टू पोरोसिटी. अगर पोरोसिटी कम है तो डिफ्यूजिविटी भी कम होगी, टॉर्चोसिटी ज़्यादा है तो डिफ्यूजिविटी भी कम होगी. बहुत सारे रीजंस इस तरह से आप उन्हें एक्सप्लेन कर सकते हो. ठीक है, आगे अगर हम और बढ़ें तो यहाँ पे इसमें और भी पॉइंट्स आ जाते हैं कि ऑप्टिमाइजेशन की बात करें, कैसे ऑप्टिमाइज करेंगे इफेक्टिव डिफ्यूजिविटी को. तो इफेक्टिव डिफ्यूजिविटी को बेसिकली इंक्रीज करना है, बिकॉज यू नो इफ यू इंक्रीज द इफेक्टिव डिफ्यूजिविटी means pore diffusion rate will increase, means more and more molecules are able to enter the pores, means more and more molecules are able to participate in the reaction, means we are able to utilize the catalyst properly up to a higher limit, so efficiency of the process will also increase. है ना. तो यहाँ पे हमें क्या करना है, फर्स्ट थिंग हमें पार्टिकल्स का साइज स्मॉल चाहिए, कैटलिस्ट साइज शुड बी स्मॉल, पोरोसिटी ऑफ द कैटलिस्ट शुड बी हाई. ठीक है, पोर साइज, पोर स्ट्रक्चर्स शुड बी ऑप्टिमाइज्ड. ठीक है, मतलब pores should be well connected. If you are having pores, the catalyst particles, if you are putting in the catalytic reactors, porosity will be there. Similarly, pores structure will be there. So जो pores हैं, that those pores should be connected properly. If those pores are not connected properly, then obviously the resistance will, the diffusivity will decrease. ठीक है, तो ये बहुत इस तरह से आप उन्हें एक्सप्लेन कर सकते हो. दीज आर सम पॉइंट्स टू एक्सप्लेन अबाउट द परफॉर्मेंस ऑफ कैटलिस्ट, टू ऑप्टिमाइज द प्रोसेस ऑफ कैटलिस्ट. ठीक है guys, तो आई थिंक दैट्स तो दैट इज मोर देन सफिशिएंट फॉर द डे. ठीक है, बाकी ये क्वेश्चन है, इसे ट्राई करना आप खुद से देखने का एक बार. अदरवाइज वी विल डिस्कस. जो आपका क्वेश्चन 6 था वो भी फिर हम नेक्स्ट सेशन में डिस्कस कर लेंगे. ठीक है, तो दिस इज द टाइम फॉर द डे. तो जाने से पहले मैं आप लोगों को एक चीज बताना चाहता हूँ, रिमाइंड कराना चाहता हूँ. यू ऑल नो 26 मई को हमारा अनअकैडमी पर एक टेस्ट हो रहा है, स्कॉलरशिप टेस्ट. तो आप अपने जूनियर्स को, सीनियर्स को, कलीग्स को, फ्रेंड्स को जो गेट एग्जाम की प्रिपरेशन कर रहे हैं इन एनी स्ट्रीम, केमिकल, मैकेनिकल, सिविल, किसी में भी, तो आप उन्हें इसके बारे में इंफॉर्मेशन दे सकते हो. उन्हें क्या, अगर ज़्यादा कुछ जानना है तो वो अनअकैडमी के नंबर पे कॉल कर सकते हैं, 8585858585. और 26 मई को ये हमारा टेस्ट होगा. हार्डली 3 days आर देयर एंड 11 AM विल बी द टाइम. 30 minutes का एक छोटा सा टेस्ट होगा. एंड ऑल द पीपल हु विल गेट गुड रैंक इन दैट एग्जाम, बेसिकली द टॉप 50 रैंकर्स ऑफ दैट एग्जाम विल गेट द स्कॉलरशिप. First 5 rankers will get 100%, then next 5 50%, then next 10 30%, और the remaining 30 will get 25%. मतलब अगर आपकी रैंक टॉप 50 में है तो आधे घंटे का एफर्ट है. उस आधे घंटे के टेस्ट में अगर आपने अच्छे से परफॉर्म किया, रैंक ले आए, तो यू हैव अ चांस टू गेट द 100% स्कॉलरशिप फॉर अन अकेडमी. ठीक है, उसके बाद तो कोई प्रॉब्लम ही नहीं. और इसके अलावा अदरवाइज इफ यू आर नॉट एबल टू गेट द स्कॉलरशिप, तो आप इस तरह से भी पूरा सब्सक्रिप्शन ले सकते हो. अभी हमारा एक ऑफर चल रहा है टिल 25 मई. 2 days आर रिमेनिंग फॉर 25 एग्जाम एंड 26 एग्जाम. तो द स्टूडेंट्स हु आर टारगेटिंग 25 एग्जाम फ्रॉम थर्ड ईयर, फाइनल ईयर और पास आउट, तो 12 months का जो सब्सक्रिप्शन है वो आपका 14,999 में मिल रहा है. 24 months का सब्सक्रिप्शन आपका 24,999 में मिल रहा है. 9 month का सब्सक्रिप्शन आपका 12,999 में मिल रहा है. ठीक है, तो वॉट एवर यू लाइक यू कैन चूज दैट ऑफर. ठीक है, आपको क्या करना है, आपको अनअकैडमी के पोर्टल पे जाना है, ऐप पे जाना है, एक नए मोबाइल नंबर से रजिस्टर करना है, और आप मेरा कोड ACE009 भी यूज कर सकते हो उसके लिए. ठीक है, यू विल गेट द अपॉर्चुनिटी टू सब्सक्राइब एंड टू गेट द गाइडेंस. ठीक है, इसके अलावा अगर आपको चाहिए तो आप अंकुर सर का कोड भी यूज कर सकते हो, दैट इज अंकुर073. डजेंट मैटर, वी आर सेम, कोई फर्क नहीं पड़ता, बट वी आर टुगेदर. तो आप जो भी कोड यूज करोगे यू विल बी एबल टू गेट आवर पर्सनल गाइडेंस. ठीक है, तो जो सेकेंड ईयर, फर्स्ट ईयर के स्टूडेंट हैं या जो थर्ड ईयर में आएंगे, तो ऑब्वियसली 26 विल बी योर मेन टारगेट. तो आई वुड सजेस्ट यू टू गेट द सब्सक्रिप्शन फॉर 24 months ओनली एट अ प्राइस ऑफ 25,000. मतलब आपके एक सेमेस्टर की फीस से भी कम है. बाकी आप लोगों की इंफॉर्मेशन के लिए, फॉर 25 फॉर द पीपल हु आर प्रिपेयरिंग फॉर 25, वी हैव स्टार्टेड आवर विजन बैच ऑन 30th अप्रैल. ठीक है, 30th अप्रैल को हमने अपना विजन बैच स्टार्ट किया था, दैट इज अ इंग्लिश बैच. एंड इन दैट बैच फ्रॉम 30th May आई एम गोइंग टू स्टार्ट अ न्यू कोर्स. CRE is already going there. Now I am also going to start a new course from 30th May, that is process calculation. Okay, the two subjects will be there, and other subjects will also be added in this batch sooner. So you will get all the 12 subjects. 30 May is the date, guys. Okay, it is for all the people who are going to see, who are willing to study in English version. प्रतिज्ञा बैच है एक, जो आपका 17 मई से स्टार्ट हुआ था, उसमें आपका ऑलरेडी मास ट्रांसफर और PC चल रहा है. एंड फ्रॉम 30th May केमिकल टेक्नोलॉजी विल बी स्टार्टेड बाय देवेंद्र सर. ठीक है, अगर आपको, एंड दिस विल बी इन हिंदी मोड. इसमें अभी मेरा PC नहीं होगा, वो हमारा बाद में होगा हिंदी स्टूडेंट्स के लिए. तो You can use my code ACE009 to get subscription for this batch. मैंने आपको बताया था, फिर से बताया, ये हमारा 26 स्टूडेंट फॉर दिस इज द बैच, नीव बैच फॉर द स्टूडेंट्स ऑफ 26 एग्जाम। आपका 17 मई को स्टार्ट हुआ था, अभी उसमें मास ट्रांसफर और पीसी चल रहा है। ठीक है, तो आई वुड स्टिल रिमाइंड यू 9 मंथ का सब्सक्रिप्शन आपका 12,999 का है, 12 मंथ्स का आपका 14,999 में है, और 24 मंथ्स का आपका 24,999 में है। ठीक है, मतलब गाइस हार्डली 1,000 पर मंथ का भी कॉस्ट नहीं पड़ रहा, और आपको सारे लेक्चर्स लाइव देखने को मिलेंगे, सभी बैचेस एक्सेस करने को मिलेंगे, सभी एजुकेटर से पढ़ने का चांस मिलेगा, और आपको अगर कोई पुरानी रिकॉर्डिंग्स देखनी है आप वो भी देख सकते हो एन नंबर ऑफ टाइम्स। तो दिस इज वन ग्रेट अपॉर्चुनिटी टू सब्सक्राइब नाउ। एंड यू कैन सी लास्ट ईयर जो हमारे स्टूडेंट्स ने सब्सक्राइब किया था या फ्री लर्नर्स थे, तो उसमें आप देख सकते हो मोस्ट ऑफ दीज हमारे 7 रैंकर्स थे जो फर्स्ट रैंक में आए थे, जिसमें से 5 हमारे प्लस कोर्स के थे, और 1 दीज 2 वर द फ्री लर्नर्स। नाउ अगर आप बाकी के स्टूडेंट्स की बात करो केमिकल इंजीनियरिंग में, तो वी वर हैविंग ऑलमोस्ट 40 प्लस स्टूडेंट्स इन टॉप 100। ये उनमें से कुछ लोगों की फोटो है, कुछ लोगों की फोटो ये आप देख सकते हो। तो अगर आप चाहते हो कि गेट 25 के हॉल ऑफ फेम में आपका भी फोटो आए, तो यू हैव द चांस टू गेट इट विद द हेल्प ऑफ, with the guidance of Mr. Ankur sir and me. We both are together here, Ankur and Ankush, again to help you. And this time, this is our target to make it 60 plus, and which will be. So this is you have to decide whether you want to be in those 60 or not. तो सोचने की कोई नीड नहीं है, दिस इज द राइट टाइम। एंड स्टिल इफ एनी वन ऑफ यू हैव एनी डाउट कि अन अकेडमी पे कैसे सब्सक्राइब करना है क्या नहीं है, तो आप हमारे टेलीग्राम चैनल को ज्वाइन कर सकते हो। दिस इज माय टेलीग्राम चैनल गेट विद एस। यहाँ पे आके आप अपना क्वेरी लिख सकते हो, आप बात कर सकते हो, मैसेज डाल सकते हो कि सर ज्वाइन कैसे करना है, क्या करना चाहिए। अगर आपका कोई डाउट है तो आई विल से सब्सक्रिप्शन लेने से पहले या तो अनअकैडमी के नंबर पे कॉल कर लो, या फिर आप डायरेक्ट एजुकेटर से यहाँ पर बात कर सकते हो। दिस इज द लिंक ऑफ माई टेलीग्राम चैनल। ओके गाइस, तो दिस इज ऑल फॉर द डे। सी यू इन द नेक्स्ट सेशन। टिल देन, bye bye, take care, have a great day ahead, and happy learning to all of you. Again, tomorrow we will come with one exciting session, one exciting questions, some new questions for CRE.